Hello everyone, welcome to our talk. Ndays are also 0 days. Can hackers launch a 0-day RC attack on popular software only with Chromium ndays? In this talk, I will introduce how we use Chromium ndays pop-up calculators in many popular software, hoping to draw attention to browser security in application software. This is our first DEF CON presentation. Let's introduce ourselves first. We are all security researchers at Tencent Security Zheng Wang. I'm Bohan Liu, mainly engaged in browser security. I'm also a Google Chrome bug hunter. And Zheng Wang is our co-speaker. He mainly engaged in browser security and kernel security. He found several bugs in Apple Safari, Linux kernel, and VirtualBox. Another co-speaker is GuanCheng Li. He is co-founder and former captain of Rekapig CTF team. He previously focused on system and software security, currently focus on LLM with security. There are 6 sections in this talk. Let's begin. First is introduction. As a browser security researcher, I researched Chromium bugs for a while and wrote many ndays exploits. And I can do a little reversing, but I know little about web security. Given those skills, can I find 0-day RC bugs in public software? And if so, what can I do to make this work easier? Now, let's take a look at how Chromium has been integrated into public software. Firstly, there is Chromium-based development, which included default mobile browsers. Second, there are browser components for various programming language. For example, the Electron framework is primarily used for software developed in Node.js, for C++, Java, and Dolphin language. CEF is also a commonly used library. Additionally, the Qt Web Engine plugins is commonly used in Qt, and Chromium may also be present in other popular sublime chains. So Chromium is everywhere in software. Based on data from CVE and Google Project Zero, Chrome may be found around 300 vulnerabilities with CVE ID each year. Of those, around 10 vulnerabilities each year are from in-the-wild attacks, and also many of those vulnerabilities can be transferred into random RC through detailed analysis. Those vulnerabilities can also be introduced into popular software through the sublime chain mentioned above. Google has an open attitude towards vulnerability disclosure, and the bug detail will be made public after being fixed 40 weeks. With the bug detail and unit test in patch, attackers can quickly make exploit code. Sometimes it's even a 0-day bug for the stable version of Chrome itself. We strongly oppose the disclosure of vulnerability details before they are fixed. But it's hard to see, hackers has a lot of priori knowledge for Chromium-based software attacks. Therefore, we conducted an experiment on some popular software to see how long the introduction of those vulnerabilities can have an impact. Let's start with the definition of RC window period. RC windows period equals the time the vulnerabilities was fixed in the software, minus the time the vulnerability was exploitable. Since it's hard to precisely determine the T exploitable, we use a new calculation method to roughly describe software's RC windows period. The method is called update gap, which is the time difference between the software's update time and its Chromium component update time. The larger the difference, the higher the likelihood of the software being exploitable during the period. In our experiment, we select some popular software on the market, including Slack, Skype, Discord, and others. The experiment was divided into 3 steps. In first step, we download the software's old version through mirror state. The second step was identify the browser component in the software, the version and the release dates. In the second step, we calculated the update gap to describe the software's RC Windows period. We use our database, which concludes over 200 POCs to assess in testing. Those POCs were used to search for high-risk exploitable vulnerabilities during the period. The final results varied greatly, with different software having update gap ranging from 9 to 800 days. Wavebox Chrome component was relatively independent and updated more frequently. On the other hand, Dropbox hardly updated its Chromium component. The rest of the software mainly used the Electron or libcf component, which most update periods over 90 days. Some softwares has a longer update period. This code has an average update time of 305 days. The shortest update period is over 70 days. As a result, many versions has a long RC period, which was demonstrated at Black Hat USA in 2022. Other software such as Slack has more frequent updates with a patch period of 30 days. However, when it hit a zero-day disclosure, they didn't deal with it in time. For example, when Chrome zero-day bug was public disclosed on GitHub on April 2021, and Slack just released its new version the day before that day. However, it wasn't until June that the bug was patched. It has a RC window period of almost 2 months. After analyzing update, we have come to several conclusions. Firstly, RC window period exists in most software, leaving attackers a period to find bugs for exploit. Second, software built on the Electron framework tend to have a shorter RC window period due to the lower code complete, which make updates easier to implement. Finally, we have observed that many companies have increased their update frequency at specific times. However, even with those effects, RC window period still exists. Let's come to attack surface and vulnerability discovery. For desktop software, developers use browser components to display specific pages and trigger certain client-side behavior in specific scenarios, making client-side development more convenient and universal. However, for hackers, during the RC window period, it's easy to launch zero-day RC attacks when they can control the loaded page. This kind of attack has many advantages for hackers, such as having many exploits with ndays vulnerabilities and no domain-specific requirements. Therefore, all hackers need to find is a situation where they can control the loading page. So, what's the scenarios that developers tend to overlook? The questions arise. What is the function of browser components? What code runs in the browser component? Let's start with how they are developed. For Electron, all codes are developed by Node.js. It's divided into main process and render process. Communicate through IPC. All code is stored in a resource folder, and there are less modification to Electron framework code. So it's easy to locate the source code. If compressed, we can also recover them from the ASAR format. As for debugging, since there are less modification to Electron framework code, most of the time we can just use command flag to open its internal development tools, like inspect or remote debugging port, just like this flag. DebugTron is a universal electron framework debugging tools. We can see here. It is also completed in this method. CEF is another popular component. Here we use libcef C++ library as an example. From the perspective of development, the code implemented by developers is divided into two parts. The privileged API function implemented by in C or C++ is used to impact client behaviors that can't be impacted by browser components. The other part is the local resource code implemented by the HTML, which is the code running in the browser component and used it to display the interface. In the development logic, it initializes first and then register the parsing and the processing logic of the privileged domain, and then register the privileged API function to form a JS object for the local resource code to call. And finally, load the local resource from the perspective of the CF library. It's actually a series of calls to exploited function. For CF, its features are it exists in the form of a dynamic link library, and the use of CF is more flexible and more check before use. A privileged API is implemented by C or C++, and the local resource code is implemented by HTML. And the location of the local resource file is uncertain, and the file may be encrypted. So, are there any common debugging methods? Yes. You can hook the API in libcef and then get and modify what we want. For example, the developer will use CF string reader create for file, CF zip reader create, or other function to load resource. We can get field location and decrypted password via hooking the info transfer between API functions, as shown here. As for debugging, although developers call CF initialize with static conf parameters, we can still dynamically modify the remote debugging port parameter to gen developed capabilities by hook. And we can also build more powerful debug tools based on development mode. Let's take a look at some cases that developers tend to overlook. First is a whitelist of loaded loads. Developers are only allowed to use the browser components to open specific pages, such as the official homepage. Other pages will be opened by default system browser, may be completed by calling shell execute open. For example, Skype has the same logic here. The first way to bypass check is page redirection. Here are three main ways: hyperlink navigation, 3OX reduction, JavaScript navigation. Its principle is that this kind of check is when handling click, and then the page was loaded in Chromium component. And the subsequent jump in Chromium will no longer trigger the check logic again. So SSO is a good pass tool, as shown in the figure on the right. The following is a demo that uses page redirection to imply RCE attack. It's an software. For security reason, all the software mentioned in this topic will not disclose the product information. Okay, after click, calculator is here. Another point is the check itself. like incorrect regular expression or an incorrect triple check. This is another real-world case. The checker uses a long regular expression. We ask ChatGPT, and run here. It told me that there are many domains easily registered by hackers can pass the check. For example, abcdjd.hk. This is the demo mentioned before. It's also an IAM software. After bypassing the check URL check, we can easily load our HTML code. We can easily pop up the calculator. In addition, another point is the special URL handler. There are two main aspects. One is the scheme registered in the system registry, and the other is the custom domain registered in the browser component. Since they are provided to domain, it's easy to miss some check while operating in them. The follow is the demo use this method. We can see that IAM software is a vulnerable area in this development case. Okay. The next is page code injection. It's a classic talk, but let's focus on the unique aspects of XSS in Chromium-based software. Here are three key differences. Firstly, XSS type. In web security, XSS typically include reflective stored and DOM-based XSS. In Chromium-based software, resources are often stored locally, so XSS in this context is typically DOM-based. Secondly, this vulnerability discovery method. In web security, the code that handles user input is typically located on the server side. So the bug discovered mainly through black box testing. However, with the code location tools we previously developed, we can white box code review in Chromium-based software. Thirdly, input source. In web security, input usually come from URL parameters or the database. In Chromium-based software, there may be fewer URL parameters, but more unique input sources, which we will discuss in next section. Based on those features, as a researcher know little web security, I mainly use the following method to discover access in local resources. Firstly, I use the tools we developed to decrypt local resources. Then, identify the unprotected resources files without CSP, and filter out input point that can be controlled. Finally, I trace whether this input can trigger code injection. This image is a real-world case I found. I have abstracted the key code, and you can see that the get URL param function processes the parameters in the URL and put them into the page using inner HTML into, finally leading to XSS. Another thing to note is that XSS vulnerability can also be introduced through the supply chain. For example, in issue 2959 of TAPRO, attackers can execute JS code in TAPRO by exploiting access vulnerability in the Mermaid library, and then use provided API to achieve RCE. We can also use the Chrome ND vulnerabilities from 2 years ago, such as CVE 2017 5070 to achieve RCE2. Here is a demo of the exploit for this case, which shows that a Chromium nday bug can also do the same things as a privileged API bug. The iframe feature is often used in note-taking or document applications to make a page display more convenient. However, when the scope of the iframe exceeds the limit, it can also cause security questions. This is more dangerous than in web security because it can be exploited without provided API or specific domain need. We also found a RCE bug in a popular note-taking software using this trick. We would have liked to release it here as an example, but it's being fixed, so we can't disclose it here. For desktop software, it may face much more complex situations than a website, such as no network or speed requirements. This requires some local cache to solve this problem. When reading or writing data, the cache is modified first and then updated with the server through communications. In this logic, the developers usually trust the cache and don't check it again when updating or loading it. Cache data can exist locally in various forms, such as a database, JSON, or a custom function format. So, how do we find them? The easiest way is to monitor the program's fail read and write operations. The image on the right shows the applications that use SQLite to store cache data. You can see that when the database content is modified, there are no validated check on the data when it's loaded, allowing any iframe to be inserted. Here is another interesting example. In a certain application, I found that when third-party components were added, the app insert an iframe here into the page, but the src attribute is strictly displayed. But in the local cache, I found a custom property called HF. I modified it to access code and reopen the program. The page was modified to any HTML code here, which means that we bypass the check by modifying the local cache. And another, when I accessed the web version of this app, I found that the web page also changed to any HTML code here. This means that the server didn't check the update of the local cache and the vulnerabilities become stored XSS. Therefore, by using the code injection, we bypass the validation and achieved RCE. And further, we polluted the server, which can lead to more remote attacks. Okay. Some applications also allow developers to develop plugins and update them to the store, thus providing more convenient extension functions. Software give plugins developers more functionality, but plugins usually need to be officially reviewed before put on the store. With the browser components, hackers may use it to bypass plugin reviews. For example, when a plugin is reviewed, the page in the plugin is a normal page. But when it's put on the market, the website is redirected to a page with expired code, thereby realizing water hole attack. The following is an example of IntelliG IDEA software. The malicious plugin is loaded. An attacker can use the browser component to achieve RCE. So when a plugin is reviewed, it's necessary by pay attention to the URL in it. Now in the video, we load the plugin. Okay. Some functions may have a arbitrary page loading process, such as the pre-rendering of crawlers or nodes. For example, the pursuit was found an RCE bug in a passive scanning function in 2021. Now, our co-speaker, Wang Zheng, will give the other part of this talk. Thank you.
Hello everyone, I'm Wang Zheng, the co-speaker of this topic. I will finish the last part. Given the short duration of RCE window period, it is crucial to develop exploits quickly. When it comes to tap vulnerabilities, a common technique is to use optimized functions to create inconsistencies that ultimately lead to tap confusion. However, for use-level-free bugs, there doesn't seem to be a publicly universal exploit method. Here, we propose a universal exploit method for V8 32-bit use-level-free bugs, which will be demonstrated in Chromium version 91. Let's start by discussing some relevant background knowledge. V8's minimal garbage collection recycles objects from the young generation, which divides memory into two spaces. Newly allocated objects are put into the from space, and when the first garbage collection is called, it identifies surviving objects and copies them from the from space to the to space, updating object pointers. Then the from space and to space are swapped, and the next round of garbage collection is performed. During scavenging, there is also an additional set of root objects, which are pointers from old space to new space objects. V8 uses red barriers to track these references. When the garbage collection identifies relevant references in the old space, it does not reclaim the objects in the new space. Here is a Chrome issue 1307610. This was caused by a missing red barrier when generating the last index object for a red expression object. When last index exits the SMI range and the red expression is in the old space, while the last index object is in the new space, the garbage collection mistakenly identifies the object as reclaimable due to the lack of reference information, resulting in a used alpha-free vulnerability. In V8, there is a type of string called 1-byte internalized string. Its memory layout is as follows. From front to back, they are the object's map, hash, string length, and the string's content. The core idea we used was to forge a string with an extremely large length and place the target object after the string in memory. Then, we can use the search method of the string to find the address of the target object after the mark. Thus, we can construct the address of primitive. Using the same technique, we can place a JS array after the fixed string. By using the string's auto bounce right, we can modify the elements member of the JS array to point to arbitrary address and achieve arbitrary memory read and write. To fix such a string, we need to create a fixed string map. V8 uses map to identify object types, so our core technique is heap spring. We can heap spring a large number of array buffer objects to obtain a stable address, and then forge the necessary members of the string map at this address. Finally, we place the fixed string in a JS array and allocate a large number of JS array objects to occupy the last index placeholder. The fixed string is placed on the left of the JS array, and a forged string object is on the right. Here is a demonstration video of our successful exploration in Chrome version 91. So, as for Chromium-based software, we found, firstly, a little bug or feature can lead to RCE attack. Secondly, there is lack of attention to the attacked path of browser vulnerabilities now. So the attack surface is relatively rudimentary, and hackers also can bypass mitigation directly using powerful Chromium bugs. This section is about how to achieve RCE attack without sandbox escape bug. The sandbox is a security protection mechanism of Chromium. Even if a hacker gets the render RCE, he still cannot get the full execution permission. This includes mandatory access-controlled environment, isolated process when HTML rendering and JavaScript execution, and finally, the limited resource access and limited IPC or kernel interaction access. The nday of sandbox escape is much less than the nday of render RCE. So how can we achieve RCE in sandbox-enabled software without a Chromium sandbox escape bug? First, let's see what's the difference between Chromium-based software and Chrome browser. The one is privileged API. It is used to implement some client-side behavior in specific cases, such as uploading files and downloading files. For renderer, it is a series of JavaScript objects. For browser, it is a series of handler code. Different frameworks have different implementations. The principle is to register some JavaScript objects in the context of the render process, and when the objects are called, we can execute the implemented handler in the browser process through IPC call. Based on this idea, there are usually two implementation logic for the privileged API. The first one checks the URL loaded by the browser component when it is initialized. If it is a specific domain, register the privileged API in the loaded context. At runtime, only the privileged domain can obtain the JavaScript object. So when we call in some function from this API, the browser processes calls it without checking the source domain. The second logic is to register the privileged API object no matter what domain it is at initialization, and then the developer can check the domain when the privileged API is called. There are some problems with both methods. For the first one, what if non-privileged web view gets a privileged context. For the second one, how to properly check the IPC access is from privileged domain. The research on electron has become relatively mature. In August 2018, Masto shared research on context isolation, which is used to isolate the context between the renderer process and preload. If this configuration is disabled, even with sandbox protection enabled, the renderer process can also call privileged functions exported from preload, such as shell.open external function. At Black Hat Asia in 2019, Luca shared his research on preload. He discovered that even with sandbox protection enabled, preload.js may still access certain native node classes and some Electron modules. Attackers can use prototype collusion to execute arbitrary IPC calls. At Black Hat USA in 2022, a sandbox bypass method was demonstrated when the renderer process could load the preload.js file in a child frame by overwriting the node integration in subframe members of the web preference of the context. We can also overwrite the context prefers context isolation and disable CISO in new renderer process. Then we can send an unauthorized IPC call with prototype collusion. We also found some interesting and wide-ranging issues with the second model, but since the vendors are working on a fix, we will share the details when it's fixed. We will make some security recommendations for Chromium-based software in two aspects. Firstly, it is necessary to update the latest version of the Chromium. Secondly, for software with high coupling, it's better to use a stable development version and introduce security patches with software updates. Thirdly, we should enable the Chromium sandbox. And last, we need to disable unused software functionalities or enable internal mitigations. For developers, we can add back-end validation and front-end rendering validation. Follow the principle of latest privilege, both privileged domain range and privileged API function. Enable universal mitigation such as CSP and be vigilant about input from unexpected sources. Here is the conclusion and takeaways of this topic. In this topic, we verify that a large number of Chromium-based software have RCE window period, and then we summarize some software attack surfaces that cooperate with the RCE window period, which makes the hackers can launch zero-day attack with Chromium ndays and give real-world examples. And we share a general V8 used after free exploit method in 32-bit, which may help make exploit faster. At last, we provide some security recommendations to help strengthen the security of Chromium-based software. At last, thanks to all the partners for their contribution to this topic. Here is the list. Okay, thanks for your listening. Here is the references of this topic. If you have any problem, you can contact us with email or on Twitter.